All right, so today we're going to look at the acceleration due to gravity. Last class we looked at the force due to gravity, which was in newtons. And this time we're going to look at the acceleration due to gravity. So let's talk first just briefly about the difference between the two. F sub g is in newtons. It's a force. The acceleration due to gravity is little g. Okay? And we know the acceleration due to gravity on the surface of the Earth is 9.8 meters per second squared. But here, in these cases, we're going to look at the acceleration due to gravity maybe at a certain distance from the surface of the Earth, or in outer space, things like that. So when we solve for the acceleration due to gravity, our unit should still be meters per second squared. It's not a force. These two are two very different things. So when it asks us for the force due to gravity or the gravitational force, we're using this variable, and we're using this equation, F sub g equals g times m1 m2 over r squared. But when it asks us for the acceleration due to gravity, we're going to solve for little g. And that's the equation we're going to work through today, is we're looking at the acceleration due to gravity. And acceleration due to gravity should always be in meters per second squared. So you do need to know the difference between those two things. They're very different things, and they mean different things. So let's look at the equations that we're gonna be able to manipulate one equation that looks like this into an equation to solve for little g. Okay. So we can find the exact acceleration due to gravity on the Earth's surface using our gravitational constant. We can also find the acceleration due to gravity at any height above the Earth's surface. Okay, and that's what we're really working towards here. But the fact that big G works in both of these equations is helpful to us. Okay, so we're going to start with our universal law of gravitation equation. I'm going to walk you through the steps that it takes to get to our little g equation here. You don't necessarily have to have this whole derivation in your notes, but I am going to walk you through how we get from point A to point B. So again, we're going to start with our universal law of gravitation equation. F sub g equals g times m1 m2 over r squared. And we're going to assume that the mass of the first object is the mass of the Earth. So all we're doing here is substituting m1 for m sub e. That's all we're doing, is that we're knowing that the mass of the Earth is going to be one of our components here. Since we're looking at the acceleration due to gravity a certain distance above the Earth or with relationship to the Earth, we're going to assume that m sub 1 equals the mass of the Earth. And we know from our last lecture that the mass of the Earth is 5.98 times 10 to the 24th kilograms. Okay, in case for some reason you didn't get that down last time, you need to have that down in your notes somewhere. Okay, our next step is we're going to substitute m times g, or mass times gravity, for our force due to gravity. Right, we talked about last time that the force due to gravity we solved for on the Earth's surface is equal to mass times gravity. So we're going to be able to plug that in right here. Okay, and since we're not using the mass of the Earth in this equation, we went ahead and put in m2, because this is the mass of our object. Okay, so mass of our object times the acceleration due to gravity would give us our F sub g that we were looking for here. Okay, last but not least, we're going to cancel m2 on both sides of this equation. So essentially here what we're saying is that we don't even care about the mass of our second object. We don't care about the mass of the person or the mass of whatever object we're looking at here. All we really care about is the mass of the Earth and the distance it is from the Earth's center. Okay, so this equation, I know it's maybe a little hard to see here, is little g, or acceleration due to gravity, equals g times mass of the Earth over r squared. Okay, so in case you can't see that, that's what the equation is. So all that we really care about here is the mass of the Earth and the distance that our object is from the center of the Earth. Remember, I'm going to say it again, that the radius here is distance from the center of the Earth. Distance from the center of the Earth. I know I'm going to say it over and over and over again, but it's very important. Okay, the radius is distance from the center of the Earth to that object. So you might have to add to it the radius of the Earth if you're given a certain distance above the Earth's surface. So let's go ahead and try one here. So go ahead and pause the video and get it written down if you need to. But what this question asks is, what is the acceleration due to gravity, or little g, on the top of Mount Everest, which is 8,848 meters above the Earth's surface? The first thing that we have to do is add the radius of the Earth to the value that's given to us, because essentially what they're telling us here is that here's our surface of the Earth, here's our Mount Everest, okay, and we want the radius of our object to be from the center of the Earth, right, r sub e, plus this distance, which is 8,848 meters. So we must add those two together. We want our whole radius to go from the center of the Earth to our object. Okay, so first thing that we have to do is add 6.38 times 10 to the 6th plus 8,848 meters. Okay, and that gives us a new radius value of 6.388848 meters. Okay, that equals our radius now, because that's the distance from the center of the Earth to the top of Mount Everest. Okay, next we're going to go ahead and plug into our equation to solve for little g, or the acceleration due to gravity. So we know that our radius we just found is equal to that value. And we're going to solve using the equation g equals big G times mass of the Earth over r squared. So we're solving for acceleration due to gravity. We know big G is equal to 6.67 times 10 to the negative 11th. We know mass of the Earth is 5.98 times 10 to the 24th over r squared. So 6.388848. And we want to square that whole term. So the reason that we're using this 5.98 times 10 to the 24th value, that's the mass of the Earth. I gave you that value in our last video, okay? And the radius of the Earth I gave to you in our last video. So those are two values that are constants that you'll be able to use a lot in these problems. So you need to have those down. This radius right here has the height of Mount Everest added to it. This is not the true radius of the Earth. This is plus Mount Everest height. Okay, so can we expect, you think, our g value, our acceleration due to gravity value, to be greater than 9.8 here or less than 9.8 meters per second squared? Okay, I hope that you're answering less than 9.8 meters per second squared. As we get farther and farther away from the surface of the Earth, our acceleration due to gravity decreases, right? We know that gravity on the moon is much, much, much smaller than 9.8 meters per second squared. So as we increase our radius, or we get farther away from the center of the Earth, our acceleration due to gravity should decrease. So let's go ahead and plug this value into our calculator and see what we get for our acceleration due to gravity. So I got a value of 9.77 meters per second squared. And I know that essentially that rounds up to 9.8, but I want you to keep that extra decimal place to show that this value is, although, pretty small, it is smaller than 9.8. It's a pretty small difference, but it still is a difference than 9.8 meters per second squared. So I want you to include that other decimal so we can see there is a small difference between those two values. So if algebraically you didn't quite get that, we're going to start down here on the bottom. Take 6.6388848 and square that. 5.98 times 10 to the 24th divided by second answer. and take that answer times 6.67 times 10 to the negative 11th. You can do it all in 3 steps in your calculator, and it's going to give you a G value of 9.77 meters per second squared. Okay. Our acceleration due to gravity values should be pretty reasonable numbers. They could be between 0 and maybe 15. It shouldn't really ever get higher than 9.8 meters per second squared as long as we're on the surface of the Earth. If for some reason we dug into the surface of the Earth, we might have a higher acceleration due to gravity value. But generally speaking, our G values should be reasonable numbers between 0 and 10. So if you're getting a G value or an acceleration due to gravity value that is much with an exponent or something like that, that means you probably plugged something into your calculator incorrectly. So now we're going to start looking at orbits of planets and satellites, things that are orbiting the Earth based purely on their force, their gravitational force from the Earth. Okay? So when we talk about satellites in orbit, we're talking about them moving in uniform circular motion. Okay, they're always at the same height above the Earth. Their orbit does not waver up and down. They're at a steady height above the Earth. They're just moving in a circular orbit, okay, a uniform circular path. So if we want to find the speed of a satellite in a circular orbit around the Earth, we're going to use this equation. V equals big G times mass of the Earth over R. And we take the square root of that whole term. V here is velocity, or speed, okay, and that should be in meters per second. Okay, this G value we know mass of the Earth, and then radius, remember, is the distance from the center of the Earth to that orbit out however far it is from the Earth's surface. So radius must be from the center to that satellite. So this is a specific satellite equation. Okay, I would make a note of that on your equation sheet. This equation is for satellites. These are for things that are floating above the Earth's surface in uniform circular motion. So this first equation was for velocity. The second equation here is to find the period of a satellite in circular orbit. So remember, period is the time it takes. Time it takes for one orbit around. Okay. So this t that we're going to be getting here, we're going to take 2 pi, and we're going to multiply it by the square root of r cubed over big G times mass of the Earth. In this instance, when we're solving for t, our value should come out in seconds. Okay? We want to find our value here in seconds, or that's what our equations will come out in. When we're solving for t in this equation, our units will come out in seconds. Okay? So let's go ahead and try some here. Assume a satellite orbits at a height of 225 kilometers above the Earth's surface. What's the satellite's orbital speed and period? Okay, so first thing that we need to do, if you want to go ahead and pause that video to get this written down, that's fine. First thing that we want to do here, I want you to notice that our satellite is orbiting at a certain distance above the Earth's surface. Okay, so here's our satellite, 225 kilometers. What do we need to do with kilometers? Okay, we have to convert that to meters, which means that distance above the Earth's surface is really equal to 225,000 meters. Okay, and we want our radius to go from the Earth's center to our satellite, so we need to add those two together. So that means radius here that we're looking for is 6.38, because that's the radius of the Earth. 6.38 times 10 to the 6 plus 225,000. Okay, not 225 kilometers. We have to convert that to meters so our units match. So that means our radius has a value of 6605 6,605,000 meters. Okay, that's our radius. It asks us for both orbital speed and period. So first things first, we'll solve for orbital speed. Okay, and to do that, we're going to use our satellite equation, which was V equals square root of G times mass of the Earth over R. Okay, and this equation is for satellites only. It's derived from one of our circular motion equations. We're not going to walk through that derivation or anything, but that's where it comes from. It comes from our uniform circular motion equations. But we're going to solve here for speed or velocity. So V equals square root of 6.67 times 10 to the negative 11th times mass of the Earth over R. Okay, so go ahead and plug that into your calculator. Hit pause, plug it into your calculator, and we'll see if we match answers here. So for speed, I got a value, or velocity, I got a value of 7,771 meters per second. You're somewhere in that range between 7,700, 7,800, somewhere in there. That's pretty good. Okay, again, I don't usually round anything in my calculator. I plug in and just keep going. I don't ever punch anything in. But algebraically, if you need help on this, I started on the top of my fraction here, so I took 6.67 times 10 to the negative 11th, multiplied it by 5.98 times 10 to the 24th. Then I hit enter. I divided by my radius. I hit enter. And then I hit second square root of second answer, and that gave me a velocity of 7,771 meters per second. Okay, now it asks for the period of this object, so I'm going to get rid of this math for velocity here. And we're going to solve for period, which is a capital T. Right, we're solving for period. So our equation for a period of a satellite is T equals 2 pi square root of R cubed over G mass of the Earth. Okay. So I'm solving for period. I'm going to take 2 pi square root of radius cubed. You want to cube that whole term over 6.67 times 10 to the negative 11th times mass of the Earth. All right, so again, go ahead and pause, plug that into your calculator, and we'll see if we match here. So for the period here of this satellite, I got T equal to 5,346 seconds. Okay, somewhere in that range. If I wanted to convert this to a little bit more usable number rather than seconds, I could convert it to hours, right? Because I know it's going to be at least 1 hour, and I'd say there's 3,600 seconds in 1 hour, and I'd get about 1.5 hours. Okay. Again, my problem didn't ask me for that. It just gives me a little bit more usable number rather than 5,346 seconds. Okay, it gives me 1.5 hours. So if you got that, go ahead and move on. If you didn't get that, I'm going to walk you through the algebra that goes with this one. Okay, so if you did get it, you can kind of skip through this next little section where I'm going through the math here. Okay, so for this value, I went ahead and took these two numbers multiplied by each other first. Okay, let me clear this out and give me some more room here. Okay, so algebraically first here, I'm going to multiply these two together, and I'm going to get T equals 2 pi square root of 6,605,000 cubed over 3.98 times 10 to the 14th. From there, I'm going to go ahead and take my radius, and I'm going to cube that, so 6,605,000, And if you hit math, you can scroll down to number 3 and hit cubed, or you can do caret 3. That gives me 2.88 times 10 to the 20th. Okay, from there I'm just going to go ahead and keep that number in my calculator, hit divide by 3.98 times 10 to the 14th, and I use the E button, right? 3.98 second EE 14. That gives me 7.23994. I want to take the square root of that times 2 pi to equal t. So I'm going to hit second square root of second answer. And then I'm going to take that 850.9 times 2 pi, which gives me 5,346.2 seconds. Okay, our next problem here asks us to determine the height above the Earth's surface a satellite must orbit if the period of the satellite is equal to the period of the Earth. Equal to the period of the Earth. So for this problem, we're looking at how long it takes for the satellite to make one complete rotation around the Earth. And when it says it has the period equal to that of the Earth, we're talking about how long does it take for the Earth to make one spin. Okay, not for the Earth to orbit the Sun. We're talking about the Earth to make one spin around on its axes. And we know the period of the Earth on its axes is equal to 1 day. So period of the Earth is 1 day. Okay, it makes one complete spin in 24 hours. But we want our period to be in seconds. So we need to take 1 day and convert it to seconds. So we're going to just do a little t-chart here. 1 day equals 24 hours. 1 hour equals 3,600 seconds, which gives us a period of the Earth equal to 86,400 seconds. Okay, which means that's also the period of the satellite. Okay, because that means it takes the satellite 1 day to complete its orbit around the Earth. Okay, we want to find the height above the Earth's surface. That's our goal here. So if we know that our satellite is orbiting at some distance above the Earth's surface, and we know that this is the radius of the Earth here, we want to find this little short distance there. At what distance above the Earth's surface? However, the radius in our problem is this whole entire distance. So at the end of our problem, we're going to have to subtract out the radius of the Earth from our radius distance that we use in our problem to find our little question mark distance here, or the distance above the Earth's surface that this satellite is orbiting at. Okay? So we want to find radius here based on the period given to us. So we are going to take our equation for the period of a satellite. T equals 2 pi times square root of r cubed over g times mass of the Earth. Alright, so I'm going to go ahead and start plugging in my numbers here. I know that T is equal to 86,400. 2 pi is always there. R is what we're solving for, so that's going to stay. And I'll take G times mass of the Earth. Alright, so if you want to try this on your own, go ahead and hit pause and try to plug that into your calculator. I'll give the answer here and then we'll work through the algebra. So for my distance above the Earth's surface, I got a value of 3.6 times 10 to the 7th meters. That's my distance above the Earth's surface. Okay, So I'm going to walk through the algebra that goes with this because this is kind of a lengthy process here to get to our final answer. Okay, so all of you might want to go ahead and watch this. If you did get this answer, great. You can probably go ahead and skip over it, but it won't hurt you to watch it just one more time. So I'm going to walk through the algebra that goes with this problem here. And I'm going to start from this equation right here. I'm going to give myself a little more room, but I'll start from this equation right here. All right, so let's go ahead and start with our problem here. Since our variable that we're solving for is under a radical, I'm going to start by moving 2 pi to the other side. So I'm going to divide by 2 pi, divide by 2 pi. Okay, so 86,400 dividing by 2, divide by pi. In your calculator, you either have to hit divide by 2, divide by pi, or divided by parentheses 2 pi. Okay, that should give you a value of 13,750.9. Okay, if you do not get this value, that means you're not plugging this into your calculator correctly, which is a problem. Okay, so you either have to hit divide by parentheses 2 pi or divided by 2 divided by pi. Okay, be very careful about that. Okay, so that leaves us with equal to square root of r cubed over, and I'm going to go ahead and multiply these two values together on the denominator of that, which gives us 3.98 times 10 to the 14th. Okay, so all I did was multiply these two values together and the denominator of that. Now to get rid of my radical, I need to square both sides. So I'm going to square this side and square this side. Okay, so in my calculator, I'm going to just take this 13,750.9 and I'm going to square it, which gives me 189087250.8 equals r cubed over 3.98 times 10 to the 14th. I don't have to square any of these numbers. All I'm squaring is to get rid of the radical. Okay, so that does not square any of those numbers. From there, I want to get r by itself. So my next step is going to be to multiply these two values together. So I'm going to take this value that's already in my calculator, this value right here, I'm going to multiply it by 3.98 E14. Okay, and that gives me a value of 7.53 times 10 to the 22nd equals r cubed. Okay, again, this value could be a little different depending on how you round, but essentially that's where we want to be, is about 7.5 times 10 to the 22nd, somewhere in that range. From there, to get r by itself, we need to take the cubed root on both sides. So we're going to cubed root both sides here. And to do that, you can hit the math button on your calculator, scroll down to number 4, hit enter. That will give you cubed root, and you can hit second answer, and that's going to pull down that 7.525 or 7.53 times 10 to the 22nd. And that gives us an r value of 4221996 equals r. Okay. The reason that we don't stop right here is because we talked earlier about how our radius goes from our center of the Earth to wherever our satellite is orbiting. Okay, so our satellite's here. It's orbiting at that certain height above the Earth. The r value that we just solved for is this entire distance. Yet our question asks for the distance above the Earth's surface. So what we need to do is subtract out here the radius of the Earth. Okay, so we're going to take this value and we're going to subtract out minus 6.38 times 10 to the 6th. And that gives me a value of 3.6 times 10 to the 7th. Very good. Now our last problem here is going to ask, what speed would that same satellite be orbiting? So from there, all we need to do is use our velocity equation for satellites. V equals square root of g times mass of the Earth over r. Okay, and what r value do we need to use here? We need to use the r value from the center of the Earth to our satellite. So not necessarily the answer to our last problem. We're going to take the step right before that. Okay, so velocity is equal to square root of 6.67 times 10 to the negative 11th over 5.98 times 10 to the 24th over 4.22 times 10 to the 7th. That was the value that we got before we subtracted out the radius of the Earth. Okay, so now we're going to go ahead and plug that in to our calculators. And we're going to get a velocity equal to about 3,071 meters per second. And that's where we're going to stop. Chapter 7 is pretty quick and easy. That's the last notes that we have for Chapter 7.